Hello everyone. So today we are going to start a very short course on functional analysis. So this will be based on a syllabus of GATE mathematics, and the idea is that we will see all the topics of functional analysis in GATE mathematics, but we will not go into proofs of the results. We will just have a understanding of the result and how to solve the questions from this exam. So here are the topics of the GATE mathematics exam. So we will try to go one by one and try to understand what does they mean and what are all the theorems, and we will not go into details of the proof, but we shall just try to understand what is the theorem, how to apply this, and let's see. So we will first start from this non-linear spaces. Non-linear space. So and we will first see the definition of non-linear space. So what is a non-linear space? So here is the definition of non-linear space. So first of all, you need a vector space. So if you look at here, X is a vector space over R or over C. Then you need a function. So first you need a vector space and then you need a function, and this function should satisfy these three properties. So what are these properties? So first is when you apply when you check the value of x under this function, this should be positive, and this is equal to 0 if and only if x is equals to 0. So this is the first property of the function. So this is called positivity property. The second is the homogeneity. So what is homogeneity? So if you multiply by a scalar, then this modulus should come out. So this is called homogeneity property. And the third is the triangular inequality. What does this mean? That means if you take sum of so if you take the value of the sum of two function, so this is if I'm saying this is a function, then I'm taking the value of the function at x plus y. So this is less than equal to value of the function at x plus value of the function at y. So this is called triangular inequality. A similar inequality you must have seen in dealing with metric spaces. So in fact this norm actually induces metric on the space x. If you look at, if you define a dxy in this fashion, then you would see that this d is actually a metric here. So in fact a non-linear space is always a metric space. So a non-linear space is always a metric space. So now we know that what is a non-linear spaces, and we will now look for some examples of non-linear spaces. And so let's see in the next slides. So now we'll start with the examples. So uh, here I will discuss some important example which occurs in GATE mathematics exam, and the idea is that if we deal with such examples, then we'll be comfortable in working in such setups. So let's start with this LP space. So what is this LP space? So if you look at collection of all the sequences, so this sequence is should satisfy certain conditions. So this is the condition. So it says that summation from n to 1 to infinity and mod xn power p is finite. And if you check this LP is actually a vector space. That means if you look at x and y which sequences which satisfy this condition, then x plus y is also satisfy this condition. That means if x is in LP and y is in LP, then x plus y, this is also in LP. That means you are adding two sequences. So this is the sequence x1 x2 something, this is the sequence y1 y2 something. So ultimately you got the sequence x1 plus y1, x2 plus y2, and so on. And then you have to see that this new sequences also belongs to LP. Okay, now that you have a vector space, you would like to define a norm on it. So norm is defined in this fashion, and you can check all these three properties here, and this is a very famous norm on LP. So from here we have that this LP is actually a norm linear space. Now what is the problem with when you take p less than 1? So if you take p less than 1, then you would see that this third property, triangular inequality, fails to satisfy. So that's why it's not a norm linear space. So your p must be greater than 1 and less than infinity. That means p should be a finite number. Now what happens if you take but you can also define a norm linear space for infinity. So the definition is that you collect all the sequences whose supremum of all xn's are finite. Supremum of this xn's is finite. That means it should be a bounded sequence. So if you take a bounded sequence, then that means if you look at a sequence x which is bounded, a sequence y which is bounded, then you take the sum, then this sum is also bounded. And similarly you can check the scalar multiplication of a bounded sequence is a bounded sequence. So that means this L infinity is actually a vector space. So now that you have a vector space here, you would like to define some norm on it, and a natural choice is this supremum. So you take the supremum of xn's, mod of xn's, and then you will see that this is actually a norm linear space. So this actually defines a norm on this space L infinity. Now that so what we know is that from p equal to 1 to infinity, we have some norm linear spaces to work with. Now next we will see some inclusion between LP spaces. So now we have L1 space, L2 space, L3, L4, LP, and L infinity. So a natural question is that do we have some relation between these spaces? So the answer is yes. So the relation is this. So L1 is actually contained in L2, and L2 is contained in LP, and LP is contained in L infinity. And this inclusion is actually strict. That means there will be a member here which is not here, there will be a member here which is not here, and there is a member here which is not here. And what is the what are the members here which are not here? You can check the sequence 1 over n. So if you take 1 over summation n square n equal to 1 to infinity, this is actually finite. So this implies that the sequence 1 by n, this belongs to L2, right? But if you take the sum 1 over n, this is actually infinite. So this implies that 1 over n, this sequence, this doesn't belongs to L1, right? So this is actually a strict inequality. That means L1 is strictly contained in L2. And similarly you can find from here to here, and to find from a sequence from here to here, you can just take a constant 1. So if you take this sum from 1 to power p, if you take n equal to 1 to infinity, then this is actually infinite, right? So that means this constant function, the constant sequence 1 is not in LP for any p, for any finite p, but because it is a bounded sequence, it belongs to L infinity. So that means what we saw is that L1 is contained in L2, L2 is strictly contained in LP, and LP is strictly contained in L infinity. So these are some standard examples of norm linear spaces, and one should be aware of this inequality, so this inclusion relation between them. Next we will see some another class of norm linear spaces which comes from continuous function. And in gate mathematics, this is a very uh, famous set of examples from there where they ask. So the very first example is the CAB. This is actually called continuous function on the interval AB. So if you uh, collect continuous functions, so you see that this is actually a vector space. And now a natural thing is to find ask what is the norm on this space. So the norm one can define to be a supremum norm. So because you know that a continuous function on the compact set AB, uh, its supremum always exists, right? So you can define this norm of f infinity, which is supremum of mod of fx x from 0 to ab, right? And you know that this is finite because f is continuous function, and you also know that this is positive, and you can check all the properties of the norm here. So you have a vector space here, and you defined a function which is a norm. So you can see that this CAB is a nonlinear space. Okay, but this is not the only way to define norm on this. So if you again consider this CAB and you define this integral form, so then you also check that this f with respect to 1, this is also a nonlinear space. So with respect to the same space, we define two different norms, this one and this one. So it is possible that there are two norms in in the same space. Okay, next is this third C1AB, and then you can see that. So what is C1AB? It is nothing but continuous function on CAB whose derivative is also continuous. So that means you took function from continuous and its derivative should be continuous. That means the function has to be differentiable. In order to find its derivative, the function has to be differentiable and the derivative should be continuous. And here you can define, so you can check that this is a vector space, and now if you defined norm on this space, which is nothing but norm of f infinity norm, that means this norm, and because its derivative is also a continuous function, so you can again define a supremum norm of its derivative, and if you add these two, then this is also a norm on C1AB. So C1AB is also a norm linear space. But from here you can see that you can talk about different norm on the same space. For example, here I have chosen 1, but you can also choose P, and then here you can take P, and then you can talk about its 1 over P power. So you can check that so for P greater than equal to 1, so you can check that this is also another norm on CAB. So on this, so what we saw is on the same space we can have different norms. Okay, so this is precisely on C01. You have supremum norm, this is called supremum norm, and this is called one norm. So on the same space you have two different norms. Okay, so today we if stop here, and we will see few more things in the next class.